Okay, today we're going to begin chapter 11 on three-dimensional space and vectors. And section 11.1 is rectangular coordinates in three space, spheres, and cylindrical surfaces. Okay, well, up until this point, we've mainly been dealing with things in two-dimensional space. So this really goes all the way back to algebra, all the way up through this point in calculus 3, two-dimensional space where we have an x-axis and a y-axis. Well, we're going to look at space here, three-dimensional space, where we have a z-axis. Okay, and the way that we typically write this, so it's a little weird because we're trying to draw on a two-dimensional surface like a piece of paper, or looking at this on your computer screen. It's two-dimensional. But we're trying to put three dimensions here in two dimensions. So how do we do this? Well, there's no perfect way to do it, but typically the way that we draw the axes are, we have the y-axis going off to the right, which is the positive y-axis going off to the right, which is a little weird because usually it's going up when we just have the x-axis and the y-axis. The positive x-axis is facing out this way, and we put the z-axis going up. Okay, now this is just giving the positive y-axis. The negative y-axis would be going off to the left. The negative x-axis would be going this way. The negative z-axis would be going down this way. Okay, so this is kind of the conventional way of writing it. So x-axis this way, y-axis to the right, z-axis up. Okay, well, if we want to locate a particular point, let's say the point 2, 5, 3 in three space, how do we do it? How do we draw the point? Well, I think the easiest way to draw the point, so it is to make a box like this. Okay, this rectangular box. So this point 2, 5, 3. And the way that you make the box is by drawing the 8 points that are on the box. So you have the origin here, which is 0, 0, 0. This point here along the x-axis is 2, 0, 0. By the way, all the points along the x-axis are going to have their y and z coordinates being 0. Okay, so this is 2 0 zeros right here. Okay, and then we draw the point 0, 5, 0 along the y-axis, and all the points in the y-axis have their x-coordinate and z-coordinate being 0. And then we draw this point out here in the xy plane. Okay, this is 2, 5, 0. So points in the xy plane, okay, those are points where the z is 0. Okay, and then you also draw these other 4 points up here. But this point 2, 5, 3, and in your mind you can kind of see this box here and see this point 2, 5, 3 out in three-dimensional space. Now, by the way, what we have here is what's called a right-handed system. This is just a convention which basically says if the x-axis, positive x-axis is pointing this way and the y-axis is pointing this way, the z-axis should point up instead of down. And the reason it's called a right-handed system is because it's the way that if you use your right hand so that your fingers, so that your palm is at the origin and your fingers are pointing out in the x direction, so flatten out your hand, and so that if you curled your fingers of your right hand, they went toward the y-axis. The position, the way that your thumb is pointing would be pointing in the positive z direction. Okay, if you'd used your left hand, you kind of have to contort your arm a little bit to do this, but if you used your left hand and did this, the z-axis would be pointing down. Okay, well, that's not all that important as far as we're concerned. Okay, on the above picture, plot the point 2, 5, 3. That's what I've done. It helps to draw a box, and the 7 other vertices of the box are these ones that I've drawn here. Okay, now there are 3 what are called coordinate planes. We have the xy plane, where all the set of all the points where the z is 0. We have the xz plane, the set of points where the y is 0, and the yz plane, which is the set of all points where x is 0. And I'll draw this here in a second. And these planes divide three space into 8 regions. These regions are called octants. So kind of like in the xy plane, you have 4 quadrants. Well, in the xyz space, in 3 space, you have 8 octants. And the first octant is the set of all points where the x, y, and z are all positive. So here, the first octant would be the octant right out here. So actually, this point here, 2, 5, 3 would be in the first octant. Now, we don't have a really convention for what's the second octant, third, fourth, fifth, sixth, seventh, and eighth, but there's no nice convention that everybody uses. But the first octant is the one that's where x, y, and z are all positive. Okay, and the x-axis here, of course, is all the points of the form x, 0, 0, y-axis, all the points of the form 0, y, 0, z-axis, all the points of the form 0, 0, z. Okay, now how do we find the distance between 2 points in 3 space? Okay, so let's look at an example. How could we find the distance from the origin, 0, 0, 0, to the point 253 that we've talked about? Okay, so I plotted the point 253. I didn't make the whole box here or anything. But the question is, what is the distance from 0, 0, 0 to 253? So I've drawn that the line segment that connects those 2 points in red here. And let's label that distance d. So how can we find d? Okay, well, I have drawn a few lines here. So we've drawn this little, it looks like a parallelogram, but actually it's a rectangle down in the bottom. And notice this length here would be 2, which means this length is 2 over here. This length is 5 because that's the length right here. And this length, this vertical distance up here, up to d is 3. Okay, so how can we find that d? Well, it turns out you can use the Pythagorean theorem. In fact, you really use the Pythagorean theorem twice to figure out what d is. So the key is to draw this little line segment here that connects the origin to this point. Okay, this would be the point 250. Okay, and notice that what we have are a couple of triangles here. We have, first of all, this triangle here is a right triangle. So I've indicated that here by this right angle. And then also this triangle right here is a right triangle. So that there is a right angle there if you think about it. Okay, so by the Pythagorean theorem we have, and we'll call this length c, by the way. By the Pythagorean theorem we have that c squared is equal to 2 squared plus 5 squared. Okay, but then we also have that d squared is equal to c squared plus 3 squared. Okay, so I've drawn that over here. Notice that we have a c squared occurring in both formulas. So if d squared equals c squared plus 3 squared, well, what was the c squared? The c squared is 2 squared plus 5 squared. So we can plug that in right there for the c squared. Okay, so these two formulas taken together imply that d squared is equal to, well, c squared plus 3 squared. But again, this is what c squared is. It's 2 squared plus 5 squared. Okay, so d will be the square root of that right-hand side. And it turns out that's equal to 38 here. So the square root of 38, which is about 6.164. Okay, so notice though, there was nothing really special about the 2, 5, and the 3. If I wanted to find the distance from the origin to any point, it would end up being the square root of the first coordinate squared plus the second coordinate squared plus the third coordinate squared. In fact, we have this little formula. Okay, as we can see from the above example, the distance from the origin to some point x, y, z would be this. Okay, d is the square root of x squared plus y squared plus z squared. Okay, now there I was giving you the distance from the origin to a certain point that we called x, y, z. What about the distance between two just any old points, two generic points, maybe neither of which is the origin? Okay, well, if we want to find the distance from x1, y1, z1 to x2, y2, z2, we have this formula. And notice it's this formula really reduces to the other formula if we allow x1, y1, z1 to be 0, 0, 0, right? So if you plug in 0 here, 0 here, and 0 here, and if you just called your other point x, y, z instead of x2, y2, z2, this formula would reduce to this formula up here. Okay, so essentially this formula is a special case of this bottom formula. Okay, and again, where this comes from is just applying the Pythagorean theorem twice. Okay, it'd be a little trickier to try to draw these 2 points, but that's really where it comes from. So let's do a quick example. How could we find the distance from 2, -3, 6 to -4, 5, 1? Okay, well, the first thing we need to do is to call one of the points, x1, y1, z1, and call the other point, x2, y2, z2. And that actually doesn't matter which one you call which, the final answer is going to end up being the same. And we just plug things into that formula. So d is the square root of -4 minus 2 squared, plus 5 minus a -3 squared, plus 1 minus 6 squared. Okay, and if you work this out, this is the square root of -6 squared plus 8 squared plus -5 squared, and that ends up being the square root of 125. Okay, so it's a little bigger than 11. Okay, so it's pretty simple to find the distance between 2 points in 3-dimensional space. Okay, now what about the midpoint between 2 points? So if I'm given 2 points, x1, y1, z1, and x2, y2, z2, how do I find the midpoint between 2 points? And let me scoot this over here a little bit so you can kind of see my picture I've drawn. Okay, so we have these 2 points here, and instead of trying to find the length of that line segment, right, the distance between the 2 points, how do we find the midpoint? point that's halfway in between those 2 points. Well, the way you do this is pretty simple. To find the x-coordinate of the midpoint, you just take the average of the x-coordinates of your original 2 points, right? And the average of x1 and x2 is just x1 plus x2 over 2. Right? The average of two numbers, you just sum them up and divide by 2. And then to find the y-coordinate, you take the average of the y-coordinates, and same thing with the z-coordinate. Now, I'm not even going to do an example. This is pretty simple here, but if you want to try it here, the midpoint between these 2 points up here, turns out it's negative 1, 1, 3.5. Okay, so you can try that, see if you get it. Okay, now also we can talk about spheres in three-dimensional space. So in two-dimensional space, you can't talk about spheres. You could talk about circles, but spheres are a three-dimensional phenomenon. And so what is a sphere? Well, every sphere has a center, okay, which we could call x naught, y naught, z naught. And every sphere has a radius r. Okay, and a sphere is just the set of all points, which we'll call x, y, z, whose distance to that center point is r. Okay, so let me draw the picture over here. So it's all the points x, y, z, whose distance to the center is r. So this x, y, z, I've drawn this particular one, but all these points on the sphere here. Okay, now we're not talking about the inside part of the sphere, like the inside part of the sphere would be called a ball. We're talking about the surface itself. There's a set of all points whose distance to the center is r. So all those points would be out here. Okay, well, of course, by the distance formula, all these points x, y, z would have to be at a distance r away from the origin, and so therefore all these points x, y, z would have to satisfy the distance formula. Right? It's the set of all points satisfying that the distance from that point to the x naught, y naught, z naught is r. And remember, this is really the distance formula, right? We used d. Let's go back up here. D was the square root of this. Well, if we do d squared, we can get rid of the square root. D squared is equal to this squared plus this squared plus this squared. Now, we're using the letter r instead of d, okay, because the r, that's the distance here. Okay, and then instead of using x1, y1, z1, and x2, y2, z2, we're using x, y, z. That's like our x2, y2, z2. And we're using x naught, y naught, z naught. Okay, well, anyways, we get this formula. Okay, the formula, again, comes from the distance formula. This is called the standard equation of a sphere. Okay, so let's look at some examples down here. So remember, the x naught, y naught, z naught, those are just numbers. Okay, so down here in this example, those would be 3, 2, 7. Okay, and I've written the r squared here on the right-hand side. So the r in this case would be 3. Okay, so this equation here, all the points x, y, z that satisfy this equation, they would be a sphere. Okay, in three-dimensional space. Okay, the center of the sphere would be 3, 2, 7, and the radius would be the square root of 9, right, which is 3. Okay, all the points x, y, z that satisfy that would be, let me move this up a little bit here, would be a sphere. Okay, now notice this is a sphere. The second one is a sphere with center -1, because this is like x minus a -1. -1, 0, -4. Now notice this y squared is like y minus 0 squared. So its center is -1, 0, -4. The radius is the square root of 5. And the last one is a sphere. So if you're to graph all the points x, y, z that satisfy this. So think of just plugging in a number for x, a number for y, and a number for z. That would all make this true. Okay, so by the way, those numbers would have to be less than 1, right? They'd have to be between -1 and 1 to plug them in. That would be a sphere. This is called the unit sphere. It's a sphere centered at the origin with a radius of 1. Okay, now let's look at an example here. The graph of x squared plus y squared plus z squared minus 2x minus 4y plus 8z plus 17 equals 0 is a sphere. Now, is that really the case? Okay, find the center and the radius. Notice that doesn't look like it's of this form here. Okay, it doesn't look like it has this form, but it turns out we can write it in that form by using what's called completing the square. Okay, so let's rewrite this equation here. So let's subtract 17 from both sides. So we get a minus 17 on the right side. Let's gather our x's together, our y's together, and our z's together. So notice we have an x squared minus 2x here, a y squared minus 4y right there, and a z squared plus 8z. Okay, well, what's another way of writing z squared plus 8z? Okay, well, using completing the square, z squared plus 8z is the same thing as z plus 4 squared minus 16. Now, why is that? What is z plus 4 squared? Well, it's z plus 4 times z plus 4. If you were to work that out, that would be z squared plus 8z plus 16. Okay, well, z squared plus 8z plus 16, if you subtract 16, those 16's go away, and you just get z squared plus 8z. Okay, now if you did y squared minus 4y, that's the same thing as y minus 2 squared minus 4. So you always take half of this number here. So here in this case was 8. We took half of it, and that goes there. Take half of it, goes here. If you and then you square it, and that's the number you're subtracting off at the end. Okay, if you do y minus 2 squared, you get y squared minus 4y plus 4. Okay, and if you subtract the 4, you end up getting this. Okay, same thing, x squared minus 2x ends up being x minus 1 squared minus 1. Okay, by the way, you always end up having a minus on the end. This could be a minus or plus right here. This is z squared plus 8z. You always end up doing half of that number there. And if it's a minus, this becomes minus in here. And if it's a plus, it becomes plus in here. But you always end up subtracting at the end. So just as some practice, try some of these. Like x squared plus 10x is the same thing as x plus 5 squared minus 25. Okay, in fact, work out that and see if that's really true. Now try these. Okay, you can try these on your own. What would be x squared plus 12x be equal to? And what would x squared minus 14x be equal to? Okay, well anyways, if we do the completing the square, notice that x squared minus 2x is x minus 1 squared minus 1. Y squared minus 4y is y minus 2 squared minus 4. And then we have the z as well. Okay, well, notice we have this minus 1, the minus 4, and the minus 16. If we add those to both sides, if we add 1, 4, and 16 to both sides, this is what we get. And the right-hand side just reduces to 4. Okay, you see the negative 1, or you see the negative 17, the plus 1 and 16, those go away. And then you were just left with 4. Okay, so notice now this is in that standard form. You can see now this is the equation of a circle where the center is 1, 2 minus 4, and the radius is the square root of this number, the square root of 4, which is 2. Okay, so it turns out though that what would have happened if this number 4 here were not 4, but what if it were a negative number? Okay, so this all kind of depended on this original 17 here, which became a negative 17 over there. If this 17 were much bigger, then we'd have a much more negative number on the right side, and it's possible that when you work this out, this number ends up being negative. Well, if you take a square root of a negative number, you get an imaginary number. So it turns out that if this number on the right were negative, what you would have would be no graph. You wouldn't even have a sphere, it would be no graph. Because notice the left-hand side can never be negative. You have something squared plus something squared plus something squared. So if this over here ended up being negative, you'd have no graph. You wouldn't have a sphere. If it were 0, you would essentially have a sphere with a radius of 0, which is really just a single point. Okay, so there's really 3 possibilities. So if you have an equation of the form x squared plus y squared plus z squared plus some number times x plus some number times y plus some number times z plus some number equals 0. And notice that's exactly what we have here. Now the g here in this case would be negative, and that's fine, and the h is negative. But anything of this form will either be a sphere, okay, or it could be a single point, or you could have no graph. And it kind of all depends on how big this j is in comparison to the G and the H and the I. Okay, the bigger J is, the bigger J is, or the smaller J is, the more likely you are to have an actual sphere. Okay, the bigger J is, you keep cranking up J bigger and bigger and bigger, you could end up getting something where you have no graph. Okay, now the one remaining thing in this section is something called cylindrical surfaces. Okay, the graph of an equation that contains only two of the variables, x, y, z, is called a cylindrical surface. Now, these are not necessarily cylinders, okay, but they're called cylindrical surfaces, okay, in an x, y, z coordinate system. So in other words, if we were going to graph z equals sine of y, now notice there's no x here. We're kind of missing the x coordinate, just z equals sine of y. How could we graph this? What does the graph look like? Well, it turns out the way you can do this is in the yz plane, you can draw z equals sine of y, right, in this yz plane. So that's this little curve here. Okay, that's kind of the dark green, this little curve here, drawing that in the yz plane. And then you essentially translate it in the x direction both ways. Now, they've only drawn part of the surface, but actually this would go infinitely far in the positive x direction and the negative x direction. This would be this wavy looking surface. Okay, and that's called a cylindrical surface. Okay, now you might wonder, why is it called a cylindrical surface? Well, one way is you do actually get a cylinder. So if I were to ask you, how would you graph x squared plus y squared equals 1? Okay, in 3 space. Now you might think, oh, that's a circle, right? X squared plus y squared equals 1, that's a circle. Well, it's a circle if you're in 2 space. Okay, you want to graph all the points x, comma, y, comma, z that make this true. Okay? Well, it turns out that the way to draw this, it's not going to be a circle. The way to draw this is in the xy plane, you could draw this circle here. Okay, and that would be all the coordinates points where the z is 0. But if you translate this circle up along the z-axis and down in the negative z-axis direction, what you would get would be a cylinder. Now, it's actually, I don't even know if you really technically is a cylinder, because it would have sort of like an infinite height. It would just keep going up and up and up and up and down, 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 down. But it has the shape of a cylinder. So that's why these are called cylindrical surfaces. But they're called that even if the graph that you get is not an actual cylinder. And in most cases, it won't be.